Alrighty, in this video I'm going to introduce you to the concept of work, specifically work done by a constant force. The main concept to get in this section is that objects require a force to move, Newton's first law, that's just inertia, and they also require work to move any distance. Now the main equation we're going to have for this section is that work equals force times distance. Specifically, it's force that is parallel to the distance. So let's actually break that equation down a little bit. Now work is simply a joule. That's the unit for it. Of course, the units for force is newtons. The unit for newtons, of course, kilograms times meters per second squared. And distance is just a meter. So when you're given a problem, you can break down everything into the fundamental units and then plug in what you actually have and solve it. So back to the concept, work has units of joules, and that will equal force, newtons, times the distance traveled. Now the two bars indicated up here, those mean that the force has to be parallel to the distance traveled. Alright, so let's go ahead and look at a box. Let's see if I can't move this fella up here. And if I can't, draw us a happy box. Happy box. I said a happy box. Sitting on the ground. Can't forget our coordinate systems. And we are going to pull on this box about that away at some angle theta from the horizon. And what we're going to do to this box is we are going to move this box some distance away. And now the box is really happy. So what is the work done to move this box? Well, let's go to our equation. Work equals force that's parallel to the distance. Well, in this equation, what force is parallel to the distance? Well, we go back to our SOHCAHTOA and we're actually looking for this component. And this component would be the cosine component. So we can break this down to our work equals force cosine theta times distance. Okay. Well, that's in the x direction. What happens if we put this in the y direction? Let's move our little thing down a little bit again. Alright. Well, now I am going to make my happy guy. One of these days I'll actually learn to draw. And he's holding our happy box. And it's too small, so now it's an equals box. Too small for me to draw a happy face. So, first off, what are the forces acting on this crate? Let's draw us a little free body diagram here. Our dot will represent our box. We've got a force of the man pushing up on it. I mean, he's just holding it there, but it is a force of, being pushed up. And we have the force of gravity pulling down on the box. So if we go back a chapter and we actually look at the sum of the forces, it's going to be equal to mass times acceleration. In this case, he's just holding it there, so our acceleration is 0. Well, this force, which equals to 0, is also going to be the sum of our forces. Ooh, can't let me forget to draw my coordinate systems. Nobody's here to yell at me, so I apologize. There's my coordinate systems. So what have we got? In the positive y direction, we have force of the push. In the negative y direction, so we're subtracting this off, we have the force of gravity. Now this all equals 0, so we can actually say that the force of the push equals the force of gravity. And we will use that in just a moment. Well, as we can see here, there's no distance moved, so obviously if we go back to our original equation for this chapter, work being force parallel times distance, if there's no distance moved, obviously it's going to be 0. Well, okay. How about we pull up our eraser here and change out this box just a little bit. And now we're going to move our box, sad box, being moved up. We'll call it 1 meter, and now he's a happy box. Alright, so our box just got moved up 1 meter. So let's look at the work being done. The work being done by the man pushing up so the work is going to equal force parallel times distance. It's going to equal the force of the push times our distance, which we said equals 1. So it's just going to be the force of the push. On the downward slope, again, this is up. And this is down. So the work on the downward side is going to equal the force of gravity times the distance traveled. Now, it's downward, so the force is in a negative direction. It's a negative force. Correct? Okay. Now let's actually look at the net force and move this up slightly. So our work net is going to be exactly what it sounds like. It's going to be the net of all forces. So in our problem where we have a force being pushed up and a force being pushed down, we are going to add the work going up and we are going to add the work going down. And that's going to be our work net. Now, if we just look back a minute ago, we have figured out, sorry about that, we have figured out that the force of the push equals the force of gravity. So let's get that back on screen here. So the force of the push equals the force of gravity. D is D, of course. So what we found out is that even though we have picked up our box and we've moved it up a meter, the man has done 0 joules of work as a net. Now the man himself, he's actually done some work, but gravity's also done work. So the net force is actually 0. Alrighty. So let's do some actual problems for your turn-in assignment. Getting some clean space here. Okay. So we're going to be looking at a box. And this box is being pulled along at an angle of 37 degrees. Let me drag that down just a little bit for you. This box is going to be dragged along at 37 degrees to the horizon. Here's our ground. Can't forget our coordinate systems. There is a frictional force acting on it of 50 newtons, and the box is pulled 2 meters. The question is, what is the work net? What is the total net work, or the total net force? So again, we are having a distance moved of 2 meters. And frictional force is acting on it of 50 newtons. Looks like we're forgetting something here. We are forgetting that our force equals 100 newtons. Alright, so let's break this down with a free body diagram. Free body diagrams make you make a little more sense of our problem. So we've got our dot representing our free body. We've got the normal force pushing up from the ground. We've got gravity pulling down. We have some pulling force that's 37 degrees from the horizon. And we've got some sort of force of friction. Alright, so remember here, the important equations are going to be work is going to equal force that is parallel with the distance, and the work net is going to equal the sum of all the individual works. Alright, so let's move up just a little bit. Little bit, I said. So what we have here, our work net, is going to be a sum of all those forces, or I'm sorry, all of those individual works. So it's going to be work done by the normal force minus, should have drawn my free body diagram a little bit lower, minus the work done by gravity, because it's pointing towards the negative direction, plus the work done by the pull, minus the work done by friction, okay, let me say real quick, there of course is two components of the force being pulled with at the 37 degrees. Sorry about that. There is a force that's actually pulling the box upward, and there's a force that's parallel with our distance that's pulling the box along. Yes, of course, the force that's pulling it upwards is actually going to reduce the normal force, which will change the value of the friction. Oh, I apologize. This is also 50 newtons. But we are given specifically in the problem that the force acting on it is 50 newtons. Or the frictional force acting on it is 50 newtons. So I can go back here, and I know because it's not flying in the air and it's not sinking into the ground, that these two, when summed together, ends up being 0. So the only thing I'm actually interested in is work done by the pull in the x direction and work done by friction, which is all in the x direction. So work done by pull in the x direction is going to be the force times the cosine of our angle theta times the distance it traveled minus the force of friction times the distance traveled. Now, what does that end up being? If we do a little math here, we end up with 100 newtons times the cosine of 37 degrees times our 1 meter, times our 2 meters, minus our 50 newtons times our 2 meters. Give me a little more room here. And we end up with 159 joules minus 100 joules to give us a work net equal to 59.7 joules. Yep, there's a 0.7 here. Sorry. Alright, so you just watched me do one, and that's the first assignment. The next assignment is going to be for you to do virtually the same problem. Now, in this problem, the only difference I'm going to have is that we're going to push the box at 20 degrees to the horizon. So, in this case, I'll go ahead and set up a free body diagram for you. If my pen would continue to work.